welcome everyone. Welcome to another installment of the NanoEducators Quarterly Forum. It's great to see some familiar names and faces, and I see some new participants. For everyone new, my name is Maria Fernanda Campa, and I'll be your MC today. The NanoEducators Quarterly Forum is a collaboration between my office, the National Technology Coordination Office, Danielle Duran at Nano and Stanford, and Mariel Kolker, a physics teacher from Morristown High School in New Jersey. The NanoEducators Quarterly Forum is a space for teachers with an interest to learn and teach about nanotechnology to come together and share resources, lesson plans, opportunities, and invite subject matter experts in topics of interest to you and your students. We're quite informal, so please feel free to interrupt, to chat, to ask questions. This is really led by you guys and by your interest. And with that, we've heard a lot of interest in nanotechnology and agriculture. So today's session, we will be discussing that topic. We have three subject matter experts, but really two main presentations, and they'll provide us with a mini crash course on nano and agriculture, tell us a little bit about their work, and any resources available to teachers at their institutions. I just click record, but just as a reminder, these sessions are recorded for future viewing, and speakers' presentations and any resources that we share today will be added to our ongoing Google document of resources. I will add that to the chat right now, so don't worry if you miss like a slide here or there or any comments. We'll have everything recorded for later viewing. Well, with that and without further ado, I will give the floor to our first speaker, Professor Yvonne Gonzalez Gamboa from the University of California, San Diego. And with that, thank you, Yvonne. Please take it away.
Thank you, Maria Fernanda. Let me start sharing my presentation. Usually have, okay, let's see. Everyone can see my slides correctly? Oh,
yes.
Okay, just trying to put everything ready. Okay, so yeah, today I'm going to be talking to you about nanotechnology in agriculture. I'm very happy to be here. Thank you, Maria Fernanda, for inviting me. So I'm going to be talking specifically of how we can use some of this nanoparticles as platforms for pesticide delivery, and in order to address some of the challenges that we have right now in agriculture. And I'm also going to try to put at the end some of the resources and some of the topics that we could cover also in an educational grounds. So first of all, why nano in agriculture? So agriculture has always been a driver force for humanity. I mean, we all need to eat. However, in the recent years, there has been a looming scarcity problem, food scarcity problem. And we have to have the plant science field to emerge with new technologies and new forms or strategies to enhance crop productivity, because we are losing a lot of our crop production per year. So there's this zero hunger goal, one of the key sustainable development goals of the United Nations. And this one talks about how we're going to have a population growth by 2050 of around 10 billion people, and how this will demand more food. So we're going to have to be able to produce 70% more food by farmers. And not only this, but not only we will have to create or produce more food, but we also have to take care of the food that we're already producing. So in order to do this, we're trying to target plant health in order to enhance food security. So one of the biggest challenges faced by agriculture right now is the need for effective pest control. So according to the FAO, we lose around 20 to 40% of global crop production due to pests, and 10% of this being to nematodes alone. So these plant parasitic nematodes are a major burden to the global agricultural industry, and they cause around a 157 billion loss per year in crop production worldwide. And this nematode that I'm showing here, it's the northern root knot, and it's one of the most damaging and widely spread nematodes. So agriculture comes from like way back, and we have done things to improve yields. As we can see here, we're trying different techniques or different technologies, trying to get into irrigation, new variety, agrochemicals, in order to improve the yield. But as we can see here, as we improve the yield, we also have an impact on the environment. And that is where nano-enabled agriculture comes up. And what we're trying to have here is getting to this efficient, sustainable part of agriculture. And three key elements or three key components that we're trying to focus on here, it's to enhance, sense, or deliver pesticides, nutrients, fertilizers in a better way in order to have this efficient and sustainable agriculture by 2080 or something like this. So the one that I'm going to be focusing more today will be the delivery part. So I'm going to be talking a little bit more about this. Okay, so our challenge here would be pesticide delivery. So while crop nematode infestation is relatively easy to diagnose, the treatment options right now are limited. So when we talk about pesticides, I just wanted to check with you. What do we think about pesticides? So just by a quick like thumbs up, thumbs down, when we think or when I tell you the word pesticide, do you think it's a good thing or a bad thing? Okay, so I see some like kind of in the middle. Okay, yeah. So when I usually ask these questions to students, I mainly get the word that they're bad. Okay, like pesticides are bad. And actually, if we think about the word pesticide itself, pesticide is actually pest killer. Okay, and we were talking in the slide before that we are losing a lot of crops due to pests. Around 20 to 40% of these crops are due to pests. So actually, it's not about not needing a pesticide, but it's needing better pesticides and also in the amount that we use them. So what happens is when we usually have pesticides and we just drop them in the ground, and these pesticides, since they're really hydrophobic, they cannot penetrate the soil well. So what happens is that they just stay in the surface and then they get eroded, or they can also go into underground currents. So we lose a lot of them, a lot of these pesticides. So the only option for us to actually penetrate the soil, since they have really pure diffusion in the soil and they're not targeted, they're lost to the environment, we need really large doses required. So in order for them to actually penetrate the soil, we need them to get aggregated and forming these clumps in order to be able to get where the pests are, in this case, where the nematodes are. So we're using really, really big quantities of the pesticide when only 1% efficiency.
Where's your earphone?
So actually, we're just only 1% of all the things that we're throwing into the environment are the ones that are getting used. So we need to find different strategies to deliver them. We need to be able to ensure that the pesticide we use at the correct amount gets to the place where it is going to be used. And that's where our nanoparticles come to play. So there are very different nanoparticles that we have. And we can use, for example, inorganic nanoparticles. This might be the most common ones. We can use gold nanoparticles, silver nanoparticles, iron oxide, quantum dots, magnetic. We can use other organic nanoparticles like liposomes that are very trendy right now, natural polymers, chitosan, etc. Or we can use also viral nanoparticles. And I focus on this ones mainly. So why viral nanoparticles? So it might sound a little counterintuitive to use viruses to try to protect plants, in this case, from other pests, while the virus itself might be considered as a pest. So what we're trying to do is to repurpose biology. So try to change this connotation of having the virus as foe and to convert him and make it be our friend. Why we use plant viral nanoparticles? Because they're very easy to produce, they're very low cost, and we can get large amounts by doing molecular farming. So one thing that we need to understand when we're talking about something applied for agriculture, it needs to be cheap. So one of the things that happen and why we're using so many pesticides and no one is, or not a lot of people are that concerned about using them because they're really, really, really cheap. So they can even use 99% more than what you would need and still be okay. The problem is maybe the part of using the pesticide is cheap, but then a lot of money it's being used in the cleanup afterwards, in trying to remove the extra chemicals from the environment. So what if we could use or repurpose some of those funds that are used for the cleanup and try to get them into like these new technologies, like the one that we're proposing here in the development of those technologies, so that we are actually just using the right amount and we don't have to do a cleanup after. And then, but it still has to be cost effective. So what we're trying to do here is, yes, we're using new technology. Yes, it's gonna like pump up a little bit the price, but it's still very manageable. It's still very easy to produce. It's still very low cost. So it still has to be cost effective. And that is why we're using these plant viral nanoparticles. And there are very different shapes and sizes. So depending on where you actually want to take the nanoparticle, what's the application, you can use these icosahedral ones that range around the 30 nanometers, more or less. We can use the tubular ones, like tobacco mosaic virus, which is probably the most known plant viral nanoparticle, the most studied one. Or we also have the filamentous ones, like potato virus X or turnmuxide virus that are this like flexuous viral nanoparticles. So the first thing we wanted to check is, we're talking about soil mobility. We're talking about delivering the pesticide to different layers of the soil because the nematode, the pest, the thing that we're trying to attack are in depth in the soil. So what the first thing we have to check is if our particles are actually able to get there. Okay, and we're trying to find like an array or a library of nanoparticles in order to like get them there. So we tried with different nanoparticles in different shapes, different sizes, different charges, and we created like this type of water saturated soil column in which we were able to check how much depth they were able to go through time. So as we can see here with the nanoparticle soil distribution of these different nanoparticles, we see that tobacco mild green mosaic virus, which is actually a close cousin of tobacco mosaic virus, was the one that was able to get farther along in the soil, 30 centimeters in depth, which is where we actually find most of the nematodes that we are trying to attack here. However, once again, I mentioned if we're trying to attack something that might be closer to the surface, maybe other shapes or other nanoparticles could also come handy. So that is why it's important to mention that this technology is tailored towards whatever you're trying to attack. So basically here, we determined that TMGMV has very good soil mobility and outperformed the other nanoparticulate systems. So our MVP, TMGMV, will be our pesticide carrier, and we're trying to use the structure that it has in order to be able to conjugate our pesticide or to conjugate our molecules to deliver. Now, we use this one because it's biosafe. It has a high low capacity. It's being produced by a company called Bioproducts, so it's very cheap. We have it in bulk. We get it in bulk. It is not transmitted by insects. That's why the biosafety cannot self-disseminate. It's not seed-borne, not pollen transmitted, and it's already EPA approved. So all the regulation part, it's already there. That is why we went to with this nanoparticle in this case. So what we're trying to do is attack the problem at its roots, and we're using kind of a Trojan horse strategy. So as we can see here, we have our nanoparticle, and this little purple dots would be our pesticide. And this one will get to the part where we have our nematodes, which are these little blue worm-like structures. So what happens? Okay, so we know that our nanoparticle is able to get to the roots area, and we know that it's able to get the pesticide there. Now, what will happen? The nematode is there. What will the nematode do? So the Trojan horse strategy comes from the nematode having in his regular diet the virus itself. So virus in its natural form, it's mostly composed of proteins. So the nematodes itself have in their diet eating these viruses. But now when they eat the virus now has the precious cargo of our pesticide, and then the nematode will eat the pesticide as well. And hopefully we would be able to eradicate it. So with this strategy, we're trying to have pest control, but also ensure food safety, because we wouldn't be using the amounts of pesticide that are currently being used. We would just be using the amounts necessary for to be able to get this pest control. So we would be increasing the efficacy of pesticide by using this nanoparticulate form, and we'll also be reducing pest growth and reducing the risk of residual chemicals along the way. So this is mostly the part that we're doing. Now, how can we integrate some of this topics or these technologies into our classes? So one of the things that and the activities that I use with my students, I've been a teacher in middle school and high school as well. So I have tried to incorporate some of the things that I do in the lab in at the university, also in my classes in middle school and high school. And I have this topic of like the virus hero, and it talks about nanoparticle functionalization. So here we use the topic of using viral nanoparticles for cargo delivery. And I talk a little bit about nanoparticulate structure, enhancing the efficiency, making them site-directed, etc. So some of the topics here precisely for the agriculture focus would be maybe talking about crop protection, take into consideration the UN Sustainable Development Goals, what I mentioned before, the Zero Hunger Goal strategy. We have to talk about economic viability. So this is one of the most important parts of whenever you're trying to design a new experiment, whenever you're trying to design new technology, you need to think about who your market is going to be, and if it's going to be sustainable in the long run, if it's going to be cost effective. Now, right now, I've only talked about pesticide delivery. However, new experiments that we've been doing are also about delivering fertilizers, delivering nutrients. So my most recent research, it's about first checking different types of soil and checking what are their needs. So there's not like a formula that we can just like give to every type of soil. So what we're checking is exactly what are their components, what do they need, and then try to deliver whatever they're missing. And for this, that's why we want to create this library or this array of nanoparticles to be able to deliver at whatever depth we need them to be delivered to. And I also like to mention this topic of repurposing biology. So right now we're repurposing, or we're changing the idea of using viruses that might have this like bad rep or bad PR recently. And we're talking about using them now for delivering something or for helping something that they usually are that they attacked, or they have this perspective that they're bad for the environment, but actually in this case they could help. This case could also be by using like silk or other components in biology that can be repurposed for other applications. And finally, the idea of functionalization or multifunctionalization. So this comes from the idea of tailoring the nanoparticle. So right now I talked about the cargo being the pesticide. However, This cargo can be any drug. It can be a pesticide, a nutrient. It can be a signaling peptide so that it can be directed to a specific site. So if you're talking about agriculture, maybe we're talking like something that will direct it to the roots, or something that could direct it to the leaves or to a specific component. But this can also be very well translated into the biomedical field, if you want to talk about that. And so all of this different stuff that you can tailor the nanoparticle with can also be translated into other fields beside agriculture. You can conjugate an enzyme, build like a nanoreactor in order to enhance a chemical reaction, or make a chemical reaction happen. You can have a tracking molecule so that you can follow the nanoparticle and see where is it going, what's it doing. Or you can also have peptides that are pH or temperature label, and you're able to release the cargo whenever you reach a certain pH. This could be soil pH, or this can be like a tumor, depending on what you're applying. And not only like the viral nanoparticles, since we have so many anchors, so different, so many ways to conjugate these different molecules, we're able to get this multifunctionalized nanoparticle. So there are a lot of ways to teach this to our students, of course, in different levels. For middle school, I have them use like actual like foam structures, and then putting the multifunctionalization, and then creating their virus hero, and them saying like, okay, this particle is gonna attack this thing, and I put a vaccine of this. So it just gives like a little creativity, and we can like put it a little bit higher for high school students, and be able to explain a little bit more of why are they choosing each or other or. So yeah, that's all I have. I want to thank everyone in my lab, Eves as well, that I think is here, my students, and Steinmetz Lab. I used to be a postdoc at the Steinmetz Lab, and I'm just starting my new lab. So yeah, that would be all, and I'm be happy to answer any questions that anyone has. Thank you.
Thank you very much for such an interesting presentation. I'll open the floor for questions. Feel free to unmute or use the raise hand motion. And while people figure out the unmute button, I have the first question. I'm curious, when students are introduced to these topics for the first time, are they surprised that viruses could be used as nanoparticles, and how do you navigate that with the students?
Yes, so the same way I asked about the pesticides being good or bad, I asked them if the viruses are good or bad. And especially due to the reason, I mean, I taught about this before the pandemic and after the pandemic. And of course, after, the answer is always yes, they're bad. So sometimes before they say like they're so cool or something like that. But now it's basically bad. So yeah, this change of perspective of you can use the different things that the virus already has. Like the virus is very good to, it's very mobile. It's very good to take things, to transport things. In this case, it usually transports something bad, something that will infect you, but you can change that and you can make it transport something that you want. So you use the characteristics, or you use the properties that the virus already has, but in your favor. So you're basically making it work for you. So if you try to change this perspective, the idea is that they could later think of other things that might have a bad like reputation, or that they think that have bad connotation in biology, and maybe think of some way that they could repurpose it and use it in our favor.
Thank you. Tracy, go ahead. Oh, you're muted.
Sorry about that. Yes, I wanted to ask you a little bit about the hydrogel ideas, if you've used any of that in your research. My sixth graders have been making them, and then we've been putting them in some potted plants to see if they're helping them grow without so much water.
Yes.
And I heard, I was reading a little bit about the fact that because they absorb water, they also absorb any fertilizer or pesticide in the soil. Has there been any, can I elaborate more about that? No?
Yeah, so actually, the way that I have used hydrogels in my research has been more for biomed and tissue engineering more than for agriculture. I've been starting some stuff in using hydrogels and having it more nanostructured by using the viruses inside the hydrogel. But yeah, so one of the uses for hydrogels is mostly because we want to, like in droughts, or to make them more resistant to droughts, to make the plants more resistant to droughts. So that we use like a coating of the hydrogel in the plants, and yeah, this could help for that. There are other research being done at UC, for example, that they use this hydrogel coating to make like robotic plants in a way. So they use them as actuators. So there are some plants that just naturally tend to like close themselves up to try to guard the water that they have, or the moisture that they have. So what this hydrogels do, they try to initiate that actuator sense, and they try to close themselves up, so that other plants that might not be naturally prone to do this would be able to do this in an area where the temperatures are rising, for example. So yeah, of course, we're trying to check if this doesn't affect the plant, like biologically, if they are able to continue like doing photosynthesis and having like living their normal life, even if they have this coat. But yes, those are some of the new stuff that we are trying with in relation to hydrogels. Yes, I don't know if I answered your question. Kind of. Thank you.
Thank you. Oh, I see another question. Camille.
Hi there. I was wondering, like, if for any reasons, let's just say, I guess, whatever reasons there are, what would be the reversal process for this technology to come back out of soils if somebody wants to revert to a natural composting way?
You mean like how would we take the virus nanoparticles out of the soil?
Yes, like let's just say that something went wrong, or for some reason somebody wanted to go back and make their soil, the land more, back in old fashioned. How would that process be reversed?
Yeah, so usually, specifically for these viral nanoparticles, we don't think of extraction process, because the viral nanoparticle itself, since it's just protein, it will degrade with time. So basically, it would just be like compost for the soil. So one of the things that I didn't mention, and that might be a question for you all, like, are these viral nanoparticles still infective? Which that could be a problem if we're thinking of putting them and just like spraying them around. This particle itself has a very small host range. That's why it's very biosafe and it's EPA approved. However, it was still infective. Nonetheless, we have the option or the possibility to remove the genetic component, the RNA, by different techniques. And this way, the only thing that stays is the coat protein, the shell, the scaffold. So, and this scaffold, as I mentioned before, it will just eventually degrade in the soil, and it wouldn't have any other like further involvement in anything there. So potentially we wouldn't have to retrieve it. And this is one of the major advantages of using viral nanoparticles or protein-based nanoparticles in comparison to using inorganic nanoparticles.
Thank you.
You're welcome.
Well, thank you. I think now it's time to give the floor to our second group of speakers, Wyatt Arnold and Andreas Backhouse from Yale University. Guys, please take it away.
Great. Let me get my screen up. Oops. Yvonne, that was a great presentation. We're probably going to touch on a lot of the same points you touched on. And so, thank you for laying the groundwork there. So hi, everybody. I'm Wyatt Arnold. I'm a recent PhD graduate from Yale University. I'm also here with Andreas Backhouse. He's also a Yale PhD candidate right now. We have been working together on some new ways of making nanomaterials recently. And as we're leaving the university setting, we're sort of starting into the idea of launching a company to sort of try and take some of this research from the lab out to the real world. And so some of these slides might be a little bit overly rhetorical at points. We're oftentimes conveying this information to people who need to be convinced. But I think there's got some good points in here as well. So I'll just start off by saying that farming is a very important sector, right? It employs a quarter of the global workforce. They use a third of the global land area. It's extremely important. And almost all of farmland is treated with some form of agrochemicals. Organic production, while it's important and oftentimes it has its place, it's only about 2 or 3% of global agriculture. And fertilizer itself is really incredibly important because without it, like half the people in this room could not be here today. Like half of the calories that we consume as the globe is supported by crops grown synthetic fertilizers. But that being said, like agriculture itself, I think is in need of some innovation. This is like Yvonne said, right? We're growing a population. We need to produce more food. But also, we're on track to miss production needs in all 4 major staple crops. Our globally, our yields are stagnating or declining due to sort of climate pressures and other issues with agriculture. And as we all know, agriculture already has some huge climate impacts. These are sort of gigaton scale impacts associated with food production, animal food production, eutrophication, things like that. And so we really think that conventional fertilizers are really highly inefficient. This can range, for nitrogen fertilizers, about 50% of what's applied is lost. This goes up to 90% for phosphorus fertilizers, and it can even be higher for some micronutrient fertilizers. Essentially, they're applied, they wash the environment. This is similar to what Yvonne said with pesticides. A lot of what applied is just sort of inefficiently used. And this can lead to sort of global ecological damage and also some really high emissions. It's more than twice the emissions of the global aviation sector. So it's a really important thing to address. And so we really think there's a need for better fertilizers right now. And this is something that I think farmers are also wanting, because fertilizer can be the largest operating cost that a farmer faces. It's a huge portion of their budget. It's hundreds of dollars per acre. And a lot of farmers are really always trying to increase their yields by using new products. And especially large farming operations are sort of the most interested in these new products. And farmers don't always have a ton of money. And so they have to have, they can't always afford new equipment. They have to have, sort of something they can apply per acre, roll out slowly. And I know, we've maybe cast farming in a little bit of a negative light here, but farmers really care about the land themselves. They don't want to cause any kind of ecological harm. They really want to preserve the land and pass it on to the next generation, even better than they got it. And so sort of being good stewards of the land is very important to them as well. And so we kind of have this idea that you need, better fertilizers that are more efficient, have less damage, and there's something that farmers, want to use. It can't be a totally crazy product that's way too much work for them. And so, there's this new field, fertilizers, which are called nanofertilizers or nanoparticle-based fertilizers. Essentially, you take a nutrient particle, you make it really small, less than 100 nanometers. Slides are moving on their own. And this small size of the particle allows it to sort of directly transport through plant cells, which leads to really efficient nutrient uptake. And sort of like Yvonne said, oftentimes these particles can be tailored and customized and engineered to have unique functionality. For example, you can make the fertilizers more rain fast by changing the particle coating, or you can make them more, plant specific by changing the size of them. There's a whole number of interesting effects you can kind of explore. And in terms of sort of making these things commercially available, sort of one thought that we have, and I would say the literature has, is that like starting with micronutrients is a really great proving ground for nanofertilizers. And that's because they're easier to make. They've been better studied. They can still offset NPK usage, which is driving a lot of these issues. And it's still thought they can generate important yield increases for farmer adoption. But I think as the hesitancy is sometimes in the room and more broadly with the public, nanomaterials, nanotechnology, especially in agriculture, is a new field. And so there's some hesitancy around it. And so starting sort of more modestly is thought to be better. And with micronutrients, you're often applying just a very small amount of a nutrient per acre, whereas something like a nitrogen fertilizer, you're applying hundreds of pounds of this material per acre. And so it's better to start with these micronutrients because as you roll out this technology, you're not sort of confronting people with hundreds of pounds of nanomaterials right off the bat, as we sort of still understand exactly their full suite of effects. And there's also been a number of studies that show that nanofertilizers, which target micronutrients, are sort of the best path forward to increasing net farm revenue, simply because nanomaterials are a little bit more expensive, and so micronutrients can be these sort of essential key targets for sort of increasing farm profitability without having to apply a whole bunch of these materials. And so I'm going to go a little bit more into micronutrients about, what they are, just because I realize not everybody is familiar with micronutrients as they are with things like nitrogen, phosphorus, and potassium. Micronutrients are important in their own right because about half of global soils are deficient in these key micronutrients, which include things like zinc, iron, manganese, boron, molybdenum. Plants need like 13 or 14 different nutrients to grow effectively. This has also led to nutrient deficient foods, which negatively impact the health of over 2 billion people. You can think about something like anemia, right, where you're not getting enough iron. The same issue applies for food grown in areas that have micronutrient deficient soils. And it's thought these crop micronutrient deficiencies are going to forecast to worsen with climate change. And sort of thinking about why micronutrients are important, there's this imagery called Liebig's Law of the Minimum, which is sort of thinking about agricultural production and the importance of those 12 or 13 different nutrients a crop needs. And the idea is that if a crop is deficient in a key nutrient, for example, like a micronutrient like iron, the crop is just not going to grow well because that's the limiting factor. Even if nitrogen and potassium and phosphorus are sort of more important generally, if a crop is deficient in a key micronutrient, it's still going to suffer, big agronomic effects. And micronutrient fertilizers right now are kind of terrible. Baseline, it's already difficult to address micronutrient deficiencies. This is because micronutrients are oftentimes metals, and metals are very prone to get sort of bound up in the soil, immobilized. They're just very finicky to deal with and dose. And so the two existing products are sort of a bulk, mineral fertilizer. This could be something like iron sulfate for an iron fertilizer. They have more than 99% of it is all lost in the environment, but they're really cheap, and so they're commonly used. Like Yvonne said, it's sort of this practice of it's cheap, so I can waste a bunch of it. And so even if it sucks, we can still maybe get 1% in there, and that'll do the job. There's sort of a newer class of fertilizers called chelates. They're more efficient fertilizers, but they're way more expensive. And they often have these drawbacks as well. So you sort of have two imperfect solutions as it currently stands. And so, we think, and I think the literature oftentimes, supports this, that nanoparticle-based fertilizers are really a solution to addressing a lot of the issues that face conventional fertilizers. This is because nanoparticles, they have really good uptake into plants through different application pathways, whether that's a foliar, seed, or soil application. They can increase crop yields by 20 to 30%, which is really huge in the farming sector. Like if you told somebody you're going to increase their crop yields by 20%, they're not going to believe you. You can have these big dosage reductions, which go a long way for addressing a lot of the environmental impacts of this technology. And also nanomaterials are generally slowly metabolized by plants, which is oftentimes a good thing because when you dose fertilizers, especially micronutrients, if you dose them incorrectly, it can cause sort of acute toxicity to the plant. And because micronutrient nanofertilizers metabolize slowly, you sort of, kind of drawing a COVID analogy, you flatten that curve of the uptake, and so there's less risk for toxicity. But again, so there's tons of research showing that these nano fertilizers are better than conventional fertilizers, but there's been a lot of issues around the manufacturing to date. And so the current sort of chemical syntheses for these are either too expensive or they're too difficult to tune to make, I think, a useful nano fertilizer. And this is because with the cost of nanomaterial production, it's not so much the cost of the input materials. Those often aren't the big driver. It's the need for really custom equipment, for really expensive equipment used for concentration and purification and quality assessment. Sometimes you use very expensive solvents. There's just a lot of inefficiencies in the process. And so essentially our thought is that you need a process that's simpler. It has to be greener because you're putting these on your food, and it also has to be low cost. But the tunability of these nanomaterials is also really important, sort of similar to what, echoing what Yvonne said. This is from a paper that's talking about, what are the main factors that affect how nanomaterials get uptaken into plants. It can be things like the size, the charge, the coating, the shape of the nanomaterials. And so there's really no single optimal nanofertilizer for all crops. And I think an analogy that's helpful here is like, if you think about a pair of glasses, right? Like if you made one pair of glasses, even if you can make tons of it really well, it's going to be useful for a very, very small segment of the population that needs glasses. But if you can customize those glasses to the unique needs of certain, individuals, they become incredibly useful. And we kind of think the same principle is true for nanofertilizers. So what we've done is we tried to improve the manufacturing of nanomaterials by developing a new sort of greener process. It's a pretty simple process. It's an aqueous process. You usually take a nutrient, which will often be a mineral form of a metal, let's say iron. You can mix it with a plant-derived compound we have. The idea here is that if you use plant-derived compounds, the whole process is greener. There's less concern about what goes on the food. You sort of heat it, and you get nanoparticle formation via this process where you form a lipid bilayer, and that helps with nanoparticle formation. And this process itself, we think that you can do. It's a lot cheaper than existing manufacturing methods. It's 90% cheaper. You can make particles that are also way more concentrated, which is important for manufacturing. And so this is sort of the technology that we've developed. And before I kind of got to this point, I don't know what Andy thought, but I kind of thought that like when you now develop a technology and you want it to help the world, you just maybe like make a patent and somebody picks it up and it helps the world. It turns out that's like not the case. You really have to like fight for it and go out there and advocate it yourself, or this technology oftentimes doesn't see the light of day. And so that's sort of what we're doing right now. We're trying to, advance this technology because we want it to have impacts, right? Like, we love doing research, but like if this is really going to change the world, it needs to get out there and you need people advocating for it. And so I think this part's going to kind of conclude our research thing. And then Andy's going to come on and present a few different like in-class lessons or experiments that we've thought about.
Yeah, so we have thought about a three-step experiment series for in-class for, I'm originally from Germany, so I'm not sure if it's middle school or high school chemistry. So the first one is based basically on soap. So olive oil derived soap. It's a very ancient type of soap. The ingredient there is sodium oleate, and you can change the self-assembly of sodium oleate. Yvonne already mentioned vesicles in her presentation. So you can go through from micelle forms, which are a couple of nanometers, to vesicles, which are up to a micrometer. And what's interesting for students here is you can really see with your bare eye a change in turbidity as you titrate, as you basically build your titration curve. And as you get to cubosomes on the right-hand side, you can then basically, in the end, flip your bottle upside down, and your initial oleate water mixture is just going to stick on the top of the bottle because it's forming like a very gel-like substance, which is a cubosome. It's a lipid bilayer connected network with water channels in between. And then that's the first one. So that only involves water and sodium oleate. 300 millimolar is the highest concentration. You can just like practically make this in like a classroom setting where you, if you do that, put it maybe in a warm water bath. Warm tap water is actually enough and disturb rate. And then the second part is synthesis. So that synthesis we can talk about because that is published. So that's a high concentration synthesis of gold nanoparticles. And here this also works with sodium oleate, so drawing on part 1. And basically by tailoring the concentration of the sodium oleate in the aqueous synthesis, you can synthesize different sized gold nanoparticles. And the nice thing about gold nanoparticles, they have these, probably you all know this nice color going from red to purple due to the surface plasmon resonance effect. And here you can then have these different colored gold nanoparticles that students visibly can see. You don't even need specialized equipment to see a change as a function of the oleate concentration. And then the third experiment, that is not perfectly connected. We would like to give you recipes for micronutrients, but these are secret sauce still. So this is a test application of gold nanoparticles on plant tissue. In a different scenario, these would be micronutrients. You can also buy commercial iron oxide nanoparticles if you want, or manganese oxide nanoparticles if you want to do this uptake experiment. And we are happy to pass these materials along if you want to turn this into a classroom experiment. With that, I think we can open the room to questions.
Thank you very much. That was great, guys. Let's open the floor for questions. Eve, go ahead.
Yes, I'm thinking about the delivery system. So if you have a field with plants, to my knowledge, nutrients come from the soil, and the aerial part of the plant will, kind of perform photosynthesis, right? So when you use nanoparticles that are so small in the soil so that the roots can absorb these nutrients, aren't you concerned that this could actually be washed out because it's so small?
Great question. Do you want me to take this one? Okay.
Yeah, so for these nanomaterials, the idea is that you're going to apply them. You can apply them a number of ways. Probably the most common way in literature, and maybe the most practical, is to apply them via foliar spray. So essentially, you mix it into water, you aerosolize it, and you essentially land it on the plant tissue. And there's sort of like a complex uptake pathway where these nanomaterials are sort of either engulfed by the cells, they can pass through the cell structures themselves, but they really can enter the plant well. And once they're into the plant, they can be metabolized within the plant tissue. And so they're uptaken sort of at the site where they're absorbed. They can also be translocated through the plant, and so they can move around and go to other areas. For example, the roots, which is maybe important for like delivering nutrients that are needed in the roots to the roots via a service application. But to your point, there is some concern that like if you make the nanomaterials incorrectly and you apply it to a plant, it might go from the leaf where you apply it, down the stem into the roots, and then plants oftentimes exude things from their roots. And so the fear is that they would exude the nanomaterials into the soil where they're sort of unused. But it's largely a function of the engineering of the particle size. So, we might find that if you make a particle that's 20 nanometers in size, 50% of it gets lost through the roots. But if we up that to, 40 nanometers, maybe the sort of movement pathway through the plant changes and, it stays more in the leaves or the stem.
And functionalization also. If
Yeah,
you want to go deeper, there's also the coating basically around your particle also dominates the translocation dynamics to some degree.
Super, thank you. Have you tested it in a real field?
We've
last year, and now we tested last year on a very small plot because we were like, if we, as two people finishing up their PhDs, how much time are we going to put in this, right? And so we did a small test last year, just to check, like, is it what we read in the literature, can we reproduce this? And we got yield values that were very similar to what the literature said. And based on that decision, then we were like, okay, we're gonna spend more time on this. And now we are here. And this growing season, we're testing with the Connecticut Agricultural Experiment Station on 1/2 acre.
Yeah. Super. Thank you.
Yeah, thank you.
Very cool. Are you guys working with Jason White and that team?
Yes.
Very cool.
Yeah.
There's a question on the chat. White and Andy, you mentioned getting more detailed copies of the lessons. Is that something that you guys can share with me and I can include it in the resource package?
Yeah, absolutely.
And we're happy to like answer more questions about those.
Awesome.
I think they're written in a way that it should work out pretty completely, but like obviously there's always context lost out, so you can reach out to us.
Thank you. Aniket, go ahead.
Thanks for the great presentation. My question is about the manufacturability and the cost of the nanoparticle from that point of view. As compared to nanoparticles used for humans, how stringent the CMC considerations are for nanoparticles for this application? Are there any less stringent considerations in terms of purification of the nanoparticles and characterization? So just want to know from that point of view, can we reduce the cost of manufacturing if the requirements are different for human use and plant use?
Yeah, that's actually a great question for the National Nanotechnology Coordination Office eventually, I think, at some point. So regulation around applications of nanomaterials in agriculture is very important. And I think maybe NNCO together with the EPA, might be bringing out some newer regulations on this. There has just been, I think last year, the EPA published, I think in Nature Nanotechnology, on how they think nano fertilizer applications and nano pesticide applications should be categorized in terms of approval processes, so that to streamline this approval process. So there's no answer on this yet, in that sense.
And maybe, maybe I heard a second part of your question, but like maybe there's the idea that, if nanomaterials for humans maybe are like a little bit stricter or more perfect or like held to a greater quality control versus agricultural nanomaterials, maybe that's a way to lower costs. And I think that could be, to some degree, but our whole idea is essentially like making the same quality of nanomaterials that you would use for, essentially human health for, plant applications, just because we think that that precision about targeting is very important. And that's sort of like why, I think we're proud of our process, is that we can get a lot of these things produced and they can be really well tuned, and it's also, not too expensive.
Thank you.
Thank you.
Any other questions? I would like to comment at Alda added more to the comment in the chat. They are very interested in the first lesson as a classroom activity for high school students. So I'll add to that. Have you guys implemented that already in a high school classroom? And is there any lessons learned or like things that you would suggest to teachers as they navigate that lesson plan?
We have not tried out this lesson before. The thought here is that it's just a very easy, safe way, I think, to like generate some nanometer sized particles. And it also has this nice, I think, as Andy was saying, the nice thing about it is that there's this really nice relationship between how these lipids form structures that's sort of pH controlled. And so it also corresponds with like a visual change. So you can say like, obviously, if you don't have a TM or something, you can't monitor if you're making a micelle or a vesicle, but there's a turbidity change in solution, which I think is like a nice, hopefully visual indicator for students that like we've reached this point and like, yes, like that's sort of a satisfying result. And then if you go further, like Andy said, you essentially get to like close to hydrogel formation. And so the whole thing, gels up, you can turn it upside down. And again, it's sort of just like maybe a few visual demarcated points that correspond with, real nanometer scale phenomena.
Yeah, and I've only done this with first year undergraduate students, so I can't say anything about high school or middle school.
But I heard the word hydrogel, so I hope that's useful for Tracy. Daniela, go ahead.
Oh, I was just going to add, just because that was actually a question that I was going to ask. So you beat me to it, Maria. But I will say that UCLA, CNSI, they actually have a gold nanoparticle experiment intended for high school students that has been run in many classrooms where high school students are very capable of going through the process of making those gold nanoparticles safely. And I think it's just really great and interesting to see how you then take the next step about, okay, once you actually engineer a material, how do you test it out in the real world in an application that's useful, and keeping in mind all those real world factors. So I think even though you haven't tested I guess it would be part 2 in terms of in a classroom making those nanoparticles, that is definitely something that is possible. I did it with my students when I taught high school.
Yeah, and I think, it's, I don't know if what method it is, but like, the citrate method is, a very common method. And I think, our hope is that ours, in a sense, is even similar than that, like simpler than that method. So hopefully even easier to use.
Thank you. Any last questions for any of our 3 speakers?
I want to.
Hi, Jamal.
I was listening. Hey, yeah, Maria. I think Queen is here also. Thank you so much, very young folks. You guys both lecture. I was listening. It's wonderful. My high school here every summer, high school students are coming, but different application. It's a solar cell. They're making different type of gold nanoparticles, silver nanoparticles, and different things. So this is interesting in agriculture. We are in energy or other medical application, but in agriculture, I would love to. Some of my friends all over the world is working with nano fertilizer, nano things. But my interest is you guys are really terrific. What I listen, all three of you, is wonderful. That especially Yvonne, that. Viral nanoparticles. That's very interesting. Maybe I would like to know more. What is more details in mechanism for this viral viral virus and nanoparticles? I mean interaction. I would like to know more and what happened in the soil. And you young two-person Wade and Andres, wonderful. We are worried about that these nanoparticles, because normal people, we are all nanochemistry research we are doing or teaching, but outside people, those who don't know about nano, they are a little bit scared about that, because I was actually editing a book, toxicology, with other three of the people. We just published it. So they are worried about that. Oh my God, nanoparticles maybe is harmful or something like that. So we have to make sure that concentration level to use, because it's in the soil, and then crops will come. Eventually, it will end up in our human body or animal body. So we have to be very careful about that. This is my comments. Nothing, no question about that. Thank you so much. You did a wonderful job.
Thank you, Jamal. Well, I think with that, I might close it up. Thank you, everyone, again for coming in. As always, I'll send an email with the link to the recording once it's on YouTube. I'll ask the speakers to send me their presentations and any resources that they want to include in the resource package. And just as a reminder, this is the last NanoEd forum of the school year. Our next session will be probably in September. And if you have any ideas or topics that you would like to discuss, please let us know. And see you guys in the fall. Bye bye.
Bye bye.
Thank you.
Thank you.
Bye.
Yes.